Our next presentation is Ozone Monitors, a deep dive into ozone monitoring, presented by David Sawyer of the South Coast AQMD.
Hello, my name is David Sawyer, and I am a Principal Air Quality Instrument Specialist at South Coast AQMD. And I'm here today to talk about ozone monitors, and we're going to do a deep dive into ozone monitoring. I like to think of ozone as sort of the granddaddy of all monitoring programs. First, I think it would be useful to talk about oxygen. And oxygen can come in different types or allotropes. Normally, it's diatomic. Sometimes it can be atomic or triatomic. Triatomic oxygen is commonly known as ozone. Ozone is an inorganic, pungent-smelling oxygen allotrope. It's much less stable than the diatomic allotrope. It's found naturally in nature when UV light and electrical discharges happen within the Earth's atmosphere, for instance, with lightning. It's a powerful oxidant and has many industrial applications related to its oxidation properties. The same feature, however, causes damage to mucous membranes in humans and respiratory tissues. I thought it was interesting during my research, I found that ozone was not always quite well understood about its negative properties. In fact, Beaumont, which is a city here in Southern California, actually had a saying that they used in the 1800s. And it was, Beaumont, zone of ozone, it will give you more energy. I wonder how many people actually moved to Beaumont after hearing that. So we find ozone naturally occurring in the atmosphere, and it's in the stratospheric layer, the ozone layer, and that's where we want it because that gives us some degree of UV protection from harmful UV rays from the sun. Where we don't want it is in the tropospheric layer, because that's where we are. Ozone forms under certain conditions. It readily forms in the presence of hydrocarbons and nitrogen oxides. And it also can be produced with a coronal discharge tube, for instance, in NOx instruments. So we're going to talk a little bit about ozone monitoring methods. And EPA has established a reference method known as the ethylene chemiluminescence method. Up until recently, there weren't any commercially available reference methods, ethylene chemiluminescence methods. However, I did see just the other day that Teledyne is now marketing a ethylene chemiluminescence monitor. But the vast majority of monitoring that you'll find is actually the equivalent method, and it's known as the UV absorption method. There are many different commercially available UV absorption analyzers out there. And this particular one is the Thermo 49IQ. You have the Ecotech Serenus 10 and the Teledyne T400, just to name a few. So the equivalent method theory of operation, as I mentioned, is based on the UV absorption method, and that's based on the Beer-Lambert law of UV absorption. And simply put, you have some different components here. You have a UV source, you have an absorption tube, and you have a UV detector. The UV detector can measure the intensity of light after it has passed through the absorption tube. And the Beer-Lambert law states that the amount of ozone in the absorption tube or in any given sample can be determined because it's known that the amount of absorption that happens is directly proportional to the concentration of ozone in the absorption tube. So now we're going to talk about the measurement cycle. This is pretty similar for all the ozone instruments out there. So gas enters through the gas inlet, passes through the particulate filter, and travels through one of two different pathways. The first pathway, the reference path, goes through an ozone scrubber where all the ozone in a sample is removed. That is drawn through a three-way valve into the absorption tube where a measurement is taken. The second pathway, the measurement pathway, avoids the ozone scrubber tube or the ozone scrubber, and through the three-way valve is once again taken into the absorption tube, and another measurement's taken. And based on the Beer-Lambert law that I mentioned before, you can compare the differences in intensity of light passing through the absorption tube. The calculation can be made, the exact concentration of ozone in the sample based on the amount of absorption. So we're going to talk about instrument components. This is the front of a Model T400 Teledyne ozone analyzer. One of the important things to note here is that you can view on the dashboard a number of the test points, and these are some of the critical parameters that need to be monitored in an ozone instrument to assure that it's working properly. This is the back of the instrument. Some of the key components here, you have a cooling fan, you have cooling fan here, you have a sample inlet, you have a sample exhaust. I think it's worthwhile to know here that the sample inlet is obviously Teflon. The only materials that are allowed in ozone monitoring are Teflon and glass. But the exhaust port doesn't matter because it's already been, the analysis has already happened, so it can be brass. The rest of these are communication ports, status ports, analog outs. Most, I think, monitoring organizations have moved to digital data acquisition, and the Ethernet port is used under those circumstances. This is once again the front of the instrument with the access port pulled open. As you can see, you can view the inlet filter. It's very convenient right there. You can see it through the glass top to tell whether or not it's dirty and needs to be cleaned. These generally need to be replaced depending on conditions about once a week. We have display boards and such here. Same thing in the back of the instrument. The rear can be pulled down and you can see the cooling fan, get access to the cooling fan, inlets, exhausts, and communication boards back here. So I've labeled some of the key components of the ozone instrument, and this is looking down on the inside of the instrument with the top removed. Key components here, once again, the sample filter right there. This is the ozone scrubber. This is the sample pump. And this is the sample bench. Now we removed the top of the sample bench so that we exposed the absorption tube in this unit. Sometimes units, I think 49i has 2 absorption tubes, double pass, and but the Teledyne T400 only has the single absorption tube. They both work on the same theory though. Absorption tube maintenance is one of the critical maintenance items, and that's why we're going to cover it first. So we've removed a sample bench from an ozone analyzer and placed it on a tabletop. And the technician here is going to remove the absorption tube from the sample bench. To do so, he's removed the 2 screws that hold the retaining ring on both sides. It's showing one of them pulled back. And after you pull back both retaining rings, you can slide out the absorption tube. And as you can see here, you've got O-rings. There's one on each end. And this is a critical maintenance item here. These do tend to deteriorate over time, and they can introduce leaks. Also, they can deteriorate so severely that they can become stuck to the side of the absorption tube, and they can become very difficult to remove at that point. So they do need to be changed out periodically. So after you have the absorption tube removed, then a full cleaning is called for. Generally speaking, you can clean these just using rinsing with DI water, pushing like a dust-free wipe or a Kim wipe through them, and or drying them with pure air. The technician here is exposing the UV lamp. A couple of things here. Generally speaking, you don't need to pull the lamp all the way out like this unless you're swapping it out, and these do tend to occasionally get unstable and do need to be replaced. But otherwise, lamp adjustments are a regular feature of this instrument in that you do need to adjust lamp intensity, and there's a whole procedure on this. So what we're looking for is lamp intensity that's 4,600 millivolts. And that's the optimal setting. Over time, it does tend to go down, and 3,500 millivolts is the minimum, and an adjustment needs to be made at that point. So to do a lamp adjustment, you need to loosen the set screw. There is an adjustment pot. You need to enter the setup procedure for reading the lamp intensity, and there's a whole section on this in the Teledyne T400 manual. And then you would adjust the lamp for the proper intensity using the gain adjustment screw. If necessary, you may need to adjust the lamp positions. This is referred to as peaking the lamp. This tends to be more of a coarse adjustment, but it may be occasionally necessary to do this as well. I want to speak about a few more preventive maintenance items. First of all, you want to replace your sample pump about every 2 years. Don't wait for it to fail. At the same time, it's good to replace your ozone scrubber about every 2 years. We've noticed a problem in some of our inland high humidity sites that are subjected to high humidity occasionally during the course of the year. During these high humidity events, ozone readings have become very erratic. We think this is due to condensation in the sample lines and possibly the instrument itself. So we've taken to raising the station temperature at our air monitoring sites, our ozone sites, to about 80 degrees Fahrenheit. This seems to have solved the problem. Recently, I also heard that EPA has approved the installation of an Nafion dryer on the inlet sample for ozone instruments. We have not used any of these, but it seems to me this would largely solve the same problem. And then lastly, you want to pay attention to your inline filters and your sample tubes. Both of the surfaces of the sample tubes and the inline filters can potentially scrub ozone. You don't want to change your inline filter immediately before calibrating your instrument. 24 hours is probably a good idea. We've even taken to running ozone into the instrument and conditioning the filter. Sample tubes, same thing. Dirty sample tubes can definitely scrub ozone and skew your readings. So the sample tubes should be paid attention to and likely cleaned or swapped out about once a year. Now we're going to talk about instrument calibration and traceability. And ozone is a very interesting gas in that there is no ozone standard. There's no EPA protocol ozone standard that you can buy in a compressed gas cylinder, similar to what you would have with SO2, CO, oxides of nitrogen. And EPA has established different levels of field and bench standards to get around this problem. They've established this pyramid of standards, level 1, level 2, and level 3 standards. The higher up the pyramid you go, the more authoritative the standard. The level 1 standard is a standard known as a standard reference photometer. And there are a number of these around the country, and they're maintained by different agencies. But South Coast Air Quality utilizes the SRP located in Richmond, California, and it is maintained by EPA at that location. And we regularly bring our level 2 bench standard to that location once a year to have it certified and verified against this level 1 SRP. The level 2 bench standard then is maintained in our headquarters, in our calibration shop, and is made available to do verifications and recertifications for our level 3 field standards. And these level 3 field standards are used to do calibrations at our ozone monitoring sites throughout the air monitoring network. So there's one additional point I want to make is that the level 3 field standards are just what they sound. They travel throughout the network to do calibrations, but you can also establish a level 3 bench standard. The level 3 bench standard would be installed at an air monitoring site, and it would be used to provide for nightly QC checks for ozone analyzers. And these are established by verifying and recertifying them against, or I should say certifying them against the level 2 bench standard located at our headquarters, and then installed in an air monitoring location. And then they are periodically re-verified by a level 3 field standard. There has been some disagreement as to the propriety of this. How can you verify one level 3 standard against another? And the answer to that is they are both certified against the level 2 bench standard. The level 3 field standard is regularly verified against the level 2 bench standard, and then the level 3 bench standard located in the air monitoring stations is simply re-verified against a level 3 field standard. I hope I said all that right. It's not, there's no adjustment made at that point. It's simply a re-verification. What is a standard actually? Well, it must comply with 40 CFR Part 50, Appendix D. It must have a way to introduce a zero air source and an ozone test atmosphere to the photometer. Generator-only devices are not allowed, and this is a change. It used to be you could certify an ozone generator and use that for testing and verifying. There are a number of commercially available standards available. And these can be in a couple of different configurations. You can have a separate generator and a photometer. This is an Environics 6100, and it's a generator-only device. And it can be paired with a photometer like this Teledyne T400. And together, it can be a level 2 or level 3 standard. It can be, your standard can be all in one unit. An example of that is this Teledyne T700U. It has a photometer and an ozone generator all in one. I'm going to talk a little bit about instrument calibration. This is a typical calibration setup. We need pure air, a pure air source. We need a level 3 standard. We need our instrument under test, and these will all be interfaced with a manifold. I'd like to talk a little bit about instrument calibration and calibration set points. Typically in the past, we would set an instrument up and run it at what we call the instrument scale, the monitoring scale. And that would be, say, for instance, 0 to 50 or 500 ppb. And then we would set up calibration set points and run a curve, and those set points would be evenly spaced throughout the instrument monitoring scale. EPA has advised that we set up a calibration scale, and the instrument can still be run at 0 to 500 ppb, but the calibration scale would be geared to run test points that are actually peppered around the area where we expect to get data, air monitoring data. In addition, each one of the test points, the calibration test points, should be chosen with a reason in mind. Here are some examples. So even though we're running an instrument at 0 to 500 ppb, we're going to call the calibration scale 0 to 250 ppb, and that's where we're going to do all our calibration work. At 5 test points, calibration test points, and this is why we've chosen each of them. 200 ppb was chosen because it's 80% of the calibration scale, and it's also our span value. Test point 2 at 150 ppb was chosen because it's our network's 3-year maximum reading. Test point 3 at 100 ppb was chosen because it's near the maximum reading at multiple sites. Test point 4, 60 ppb was chosen because the NAAQS 8-hour, it's the NAAQS 8-hour ozone standard, and it's also our 1-point PC check. And finally, test point 5 was chosen at 20 ppb because it is near the published MDL for the instrument. This is our ozone calibration spreadsheet that we used at South Coast. EPA has published a recommended spreadsheet for doing calibrations. We opted to continue to do our own and just incorporate all of the requirements as we understood them into our calibration spreadsheet. So I'm going to go through some of the aspects of this spreadsheet. There's a lot of information here. So this is an as-is calibration, and it was performed in December of last year at Los Angeles. The analyzer under test is a Teledyne T400. And these are the instrument factors. What we used to call a CTS now is a level 3 field standard, is a thermo, and it's actually a 49i, and the factors are listed here. So as I mentioned before, we set up 5 calibration set points on our calibration scale, 0 plus 5 points, 200, 150, 100, 60, and 20. We take 10 readings off of our level 3 bench standard just to make sure that the instrument is settled down. You can see it's very stable here. And we take an average and apply the instrument calibration factor, again, for our standard. And this is the resulting reading from our instrument under test. And then we've got to do a number of statistical assessments here. The spreadsheet will calculate a best fit line based on the results from our instrument under test. And it will look at the point difference of each point from our best fit line. And it will also calculate a percent difference from each point off our best fit line. Then overall, it will calculate the slope between the instrument and our true reading as generated by the level 3 standard, the CTS line right here. So we're looking at a couple of things for our instrument to be a successful calibration. The standard as is equals final needs to be plus or minus 3 ppb or 2.1% for all points. So you can see here, plus or minus 3 ppb is met at each one of these points, no exceedances. The second test is an or, so it doesn't have to be both of them. It can be either or, 2.1% for all points. And as you can see, we're less than 2.1% for all points. And finally, it needs to be a slope of 1 plus or minus 0.05 for it to be a successful calibration. Our slope calculation here is 1.02. That's a deviation of 2.75%, and we passed there. And so this is a successful calibration. We've got some other interesting pieces of information here also, correlation, and then change from last final. So it did change 2% from last final, and that's an acceptable reading as well. So now that's it for me. And I hope all of your calibrations are successful, and happy ozone monitoring.
Great. Thank you, David, for that presentation. If you could go ahead and join me. Oh, there you are. I've got some questions here, and there were also some questions that were typed.
Before you get to your questions, I kind of wanted to make one quick point that maybe I should have made during the presentation, and that's that most of the preventive maintenance items that I listed, we try to do once a year, and some of the items you only have to do every other year, but we try to do them at the beginning of ozone season, somewhere in like April or May. And the idea is that we can start out with a fresh instrument, have the instrument work trouble-free, through ozone season, so we don't have any downtime. We don't have to do any calibrations, that we can just run it straight through and get as much data capture as possible through ozone season. That seems to work pretty well for us.
All right, so first question here. Hi, David, great presentation. If your analyzer is set to a range of 0 to 500 ppb, do you hit cal, span, enter at a concentration of 200 ppb?
That is correct. Yeah, we pretend by all intents and purposes that the instrument is running at the calibration range, even though it is running at a higher range. So, you know, we do the calibration set. I think I said it's 200 ppb, but yeah. And then all the points are in that calibration range as well. So we essentially ignore the upper range of the instrument. The instrument will capture data that happens to go above that, but it, you know, it's not, we're not getting data above that range anyway.
All right, Hansa says, changing or cleaning the sample line only once per year might not be frequent enough, especially at stations that have experienced wildfire smoke or other pollution. Many air monitoring organizations clean their sample train monthly. These air monitoring organizations pass QA audits without issue. The ozone-only sites at national parks have their filter at the inlet. This keeps the sample line clean. Also, sending nightly precision and spans through the probe is a way of monitoring for ozone scrubbing in the sample train. This helps the operator decide when to clean the line. What are your thoughts?
Yeah, I think you always have to gauge your preventive maintenance depending on the condition that the site is subjected to. And certainly when in years past, when we've had you know, pretty intense wildfires, you know, we just get right into the maintenance of the instrument after that, because we're pretty sure that the sample lines and the instrument probe and even possibly the instrument have been affected. So we just act accordingly under those conditions.
Great. And our next question is from Nicole. What does the stability measurement mean on the ozone analyzer dashboard, and what should it be reading during a calibration?
What is, say it again, what is the stability measurement?
The stability measurement.
Yeah, that's something that I guess you could say that the Teledyne has sort of programmed into the instrument. It just simply won't allow for you to do like a calibration adjustment unless the stability is arrived at. So in other words, if you're changing your concentration, your challenge concentration, so the instrument is rising or falling, you know, it won't let you like calibrate the instrument or adjust the calibration of the instrument. It has to be essentially stable before it even allows you to do that, I believe.
Okay, and any pointers to avoid contamination of sample tube after a cleaning?
I'm not sure how it'd be contaminated. I mean, you know, we dry them using the station pure air. So, you know, and if it's not to be used right away, it'd be a good idea to cap both ends, I think. That's all I could really offer.
I see a question in the chat. Please repeat, when is ozone season?
Well, our ozone season is essentially June, I mean, through pretty much into October. I mean, that seems to be sort of changing over the years. It seems to be getting somewhat later in the year, but it really doesn't start in earnest until July. But we consider our ozone season from June into like mid-October, essentially. But the whole point I was trying to make just a minute ago was to do the instrument maintenance, you know, prior to the start of ozone season, so we can just have, you know, nothing but monitoring going on during the course of ozone season.
And what ozone levels are used for nightly precision checks? Do you scale up or down?
I'm not sure what the question, do we scale up or down? Yeah, I don't know. I'm not sure what that question is. We do have a specific, I think it's 0.06 is what reason. I have to check on that. Yeah, I would have to verify that. I think that's what we're using.
Well,
Say 60 ppb, in other words.
I don't see any other questions, and we are out of time for this session. So our next session is going to be at 9:35. So we do have a break right now until 9:35. So thanks, David.
You're welcome.
All right. Bye-bye.
Bye-bye.